Okay, that was the wrong button. I meant to hit, well, I'm doing this the longest way possible today. There's a button here for present. That's not it, from the beginning. All right. We studied chapter 3, two-dimensional motion on Monday. In lab, we once again were looking at graphs, this time looking at acceleration versus velocity graphs. And today, according to schedule, I'm jumping straight to chapter 4 today, but I'm actually going to lecture just a little more on chapter 3 before I start on chapter 4. And then we're going to start in chapter 4. Now, remember, we have exams, and now that we're about 20% of the way through the semester, it's time for our first exam. So we'll have our first exam on Tuesday during the lab period next week. So there's no pre-lab quiz for next Tuesday, since there's going to be a test during the lab period instead of lab. You'll have 2 hours to do the test. So you're also going to get out of lab an hour early. I've already talked about what's going to be on the test, and I'm going to review for the test on Monday, the day before the exam. The material on the test is only through chapter 3. So I'm going to do 2 problems in chapter 3. Hopefully that doesn't take the whole class period. And then I'm going to start on chapter 4, and on Friday I'm going to be lecturing on chapter 4. So the stuff on forces will not be on the exam. The reason I have that delay is so you have some time to think about this stuff and go through the homework and feel more comfortable with it instead of, well, I did homework on it, now I've got a test on today as well, right? I want you to have a little gap there for reviewing it. So, like I said, on Monday, I'm actually going to talk about the exam and go through some problems and that kind of thing. But right now, things that would be beneficial for preparing, the worksheets, actually, I think I have the solution on OneNote for the problems because that's where I did the solution that's on YouTube for the worksheet. But the worksheets are probably your best resource for preparing for the exam. The upper section is just rote knowledge. It's like fill in the blanks with the right words. It's not going to be fill in the blank in the test. You're going to have multiple choice to check rote knowledge, and so that should really help you with that type of material. Then it has, I think there's 2 problems on the one for worksheet for chapters 1 and 2. And hopefully by tonight I'll have the worksheet for chapter 3 done. And then the problems, like I said, you can look at YouTube to see the solutions, me working out the solution and explaining how I'm doing it. And those should help you in preparing for the problems of the test. Oksana had a question.
Yeah, I was wondering, the worksheets are the OneNote?
Well, the worksheets are on OneNote as well as, I'm pretty certain, somebody talked to me about it, I'm pretty sure I put it on Moodle as well. The one on Moodle would be with no writing on it. The one on OneNote, I think, has writing on it.
Okay.
Remember also, you have review the chapter summaries for each chapter and works the problems. There's really nothing that helps you to figure out how you apply the concept than looking at a new problem and thinking, okay, what are the concepts? How do things fit together? At this point, our concepts are very simple. It's just applying them that gets hard. But working problems. So there's review problems or practice test problems, I think is what I call them, on Moodle. That's another source of things. There's a bunch of old exams. I post all the exams and leave them there, so you have like 3 or 4 years worth of exams there. And then remember, there's tutoring right here with DJ tomorrow from 7 to 9. Russ? Excuse me? What?
Where to?
Oh, because I've rearranged, the section with assignments is really, really big, and then underneath that. Okay. All right. This is an equation. It's called the range equation. This is one equation that you will not have on the exam. The reason you won't have it on the exam is that's a special case equation. That's only correct if you have something that starts and ends at the same elevation. Now, that's reasonably common, like you kick a soccer ball, it started at ground level, it ends at ground level, right? To a good approximation, if you fire a cannon, it starts at ground level and ends at ground level. In reality, obviously, it started maybe a meter above ground level. And in cases where it starts and ends at the same elevation, this equation will give you the distance it travels with what assumption?
No,
Okay, no air resistance, so no air. And we also are, what was the other thing I was going to say? Oh, yeah. And assuming constant acceleration, which if it's in free fall, it should be. So this is an equation that actually relates best to the the simulation we did in class on Monday with the motorcycle jumping. Because you can then calculate, okay, I have this distance it needs to be. If I'm going this speed, what does the angle need to be? Or if I have this angle, what does the speed need to be? Or if I have this speed and this angle, how far is it going to go? That's the utility of this. This equation comes from doing the work like I'm going to do on the next two problems for the special case where y final is equal to y0. So I'm just showing this to you, and I will make one more comment that we saw from the demonstration or the simulation in class. 45 degrees gives you the longest possible range if it starts and ends at the same elevation. Not true if it starts and ends at different elevations. So if you go steeper, it'll go shorter distance because it's going higher, spending more time in the air because it's going higher, but has a smaller horizontal component for its velocity. If you go at a flatter angle, it's not in the air as long, but it's going faster horizontally. And so you can get the same distance through a steeper angle or a flatter angle. And the difference is how long it's going to take you. Now, let's say that you're playing baseball and you're an outfielder. You've got the runners rounding, well, halfway between second and third if you're going to have a reasonable shot here. When you scoop up the ball in the outfield, so you want to get it to home plate as fast as possible. They tell you not to throw it on the fly, right? You're supposed to throw it so the cutoff man can cut it off or let it through. But let's just say you're throwing it on the fly at home plate because you're that kind of person. You have two angles that are going to get it right there at the catcher's mitt. One that goes higher and one that goes lower with your speed you can throw. Which one are you going to choose? The lower because it's going to get there faster. Right? So there are some times when you definitely make the choice between it. If you're shooting a basketball, which is going to be the second problem we do today, which one would you want to choose? Why the higher?
So you don't get blocked.
Because it's going to be, well, okay, there's that too. There's that too. From a physics standpoint, there's no way blocking your shot. In fact, the problem I'm going to do is shooting free throws. Nobody's going to be swatting your free throws. But you want the higher because it's going to be dropping down straighter, so it actually is, less likely if you're off by a little bit to miss. Okay, Russell, you had a question.
Yeah, what's an outfielder?
What's what?
What's an outfielder?
An outfielder is a person in baseball who is standing far away from home plate. All right, so our first problem is dealing with baseball. Now, if you want to see a bunch of cool, nerdy stuff about baseball and about the speed the ball comes off the bat and how fast batters hit the ball, that's a cool website. Air makes a huge difference for the distance that a baseball flies. Did I show you this graph before?
No.
No, okay. So this here is taking one particular trajectory. This angle here is well below 45 degrees. It's not going to be the angle that gets it the farthest. When I was a kid, I used to get really discuss it with people who hit towering fly balls even when they're home runs. And I'm like, you got to go flatter so it goes farther because I didn't know my physics. But hitting it around 45 degrees, which coming off the bat looks like it's a pop-up until it just keeps going because you hit it really hard, is going to get you the longest distance you can fundamentally, especially because the outfield fence, a little bit above 45 is actually going to get you the longest because the fence is higher than where you hit it from. This here is more like 30-degree angles that came off the bat, so it's not the longest distance you can get from the speed the ball came off the bat. But you see there's like a 70% of the vacuum trajectory is what you get with air. So air is going to make it go a much shorter distance. My calculation, of course, is going to be pretending there's no air. No air, not error. So I have, assuming that you have an exit velocity of 103.6 miles per hour. Where did I get 103.6 miles per hour? That, actually, I think it was in 2013 or something, was the average speed of the ball coming off of the bat of a Major League Baseball player. So I just took the average speed the ball comes off the bat for a Major League Baseball player. And you have an angle of 42.5 above horizontal. So that's coming off higher than this. It's still less than the 45 that if it starts and ends at the same elevation would be optimal. So it's going to be, not exactly the optimum range, but pretty close to the optimum range. And the question is, how far is this ball going to travel before it hits the ground? So if you're doing this problem, and of course I'm going to switch to OneNote for actually doing the problem. If you're doing the problem, the first thing to do is to make sure you understand the question. So what are we looking for? Okay, how far the ball travels. Before we start, I should draw a picture, right? And see, yeah, always. So, how careful should I be? I think that's the one that'll. Right. Okay, there's my X and Y axes in a beautiful color. So I wasn't thinking. There, now it's the regular color. So I'm going to have the ball start here at some elevation. It's 0.5 meters. And it's going to go up at an angle of 42.5 degrees and come down like this. And so I'm going to write in on here what I know. That was a nice horizontal line. .3 meters per second is what that comes to be in the metric units. Okay, there I've written down all of the numbers that are given to us in the problem. But there's one more that we know that's not written down. What's the one more that we know that's not written down? The acceleration of gravity. So I'm going to have acceleration in the y direction is equal to minus g, or minus 9.80 meters per second squared. Those mean the same thing. All right, so I've got all of the stuff that's known drawn on there. Now let's go for stuff that is not known but that is relevant for the problem. And I'm trying to figure out what color to make this in. I guess blue. We're looking for that x final. I'll arbitrarily say x initial is 0. Now I have to think about how to solve this. I've got everything laid out. How do I solve it? First is what concept, and right now your concepts are very limited. What concept is involved with this problem? Okay, range.
Acceleration, velocity.
Okay, acceleration, velocity. I combine these all and say it's kinematic equations is how I'm going to solve this. It's a kinematics problem. So I'm going to use the kinematic equations. Now I'm not going to write out all the kinematic equations. I'm going to think about which ones I want. But my concept here is use kinematic equations. And because this is two-dimensional motion, I need to break into components, right? Now the next one is less obvious than the ones above. When I break them into components and solve them, what is the same for both the horizontal direction and the vertical direction? There's one variable that's the same for both horizontal and vertical motion.
Oh, range.
The time. The time is the same for both. So solve one for time. So there's the method I'm going to use right there. And that's the real physics. Now, it's still a physics problem as you do the math. But the real physics is the thinking through, how can I get my answer from this? Now, if I say break into components, there's one more thing I need to add to my figure, and what's that? Yes, I need to put in the directions. So that's going to be my x direction. That's going to be my y direction. Now x and y will make some sense instead of being, I don't know exactly what they mean. So break into components. So here's going to be my x direction and my y direction. X initial, the starting position, starting at 0. X final equals, I don't know. That's what I'm looking for. Vx initial, AX. Okay, so what is the initial speed in the x direction? 46.3 meters per second is the initial speed, not the x component of it.
Assuming you need to like throw triangles.
That's
Yes.
the 46.3.
Change the. I'm trying to change the color. It doesn't like me to try to change the color, so forget it. We won't change the color then. We'll just put red for that. Seriously. Okay. There's my x component. There's my y component. So the hypotenuse is 46.3 meters per second. And so then I have to just ask myself, okay, which side is Vx initial? Adjacent or opposite? Adjacent. And therefore, that's going to be the hypotenuse times cosine of the angle. And that means that Vy initial is the opposite side. So that's V0 sine of 42.5 degrees. Now, how does me saying it's opposite side mean it's sine? Because sine theta is opposite over hypotenuse. And since the hypotenuse is what we know, then it's opposite and hypotenuse I'm relating. Sine is the one that does it for me. And so you should not jump to these unless you're already comfortable with sine of theta is equal to opposite Vy0 over hypotenuse V0. And so with that division, then you multiply both sides by V0 and you get the equation I wrote. So if we do these calculations and whoops, to save me time, I did them already. So if I put in my numbers, my 46.3 meters per second cosine 42.5, I see students working on them, so I'm going to ask you so you can, pop them out. What did you get, Anna? So you said
One, yeah, that's
Vx initial is 34.14 meters per second. What is the acceleration in the horizontal direction? 0, right? We chose vertical and horizontal. I didn't say y this time, but we chose them so the acceleration was all in the y direction and none in the x direction. Any other choice would have made the work just harder. We're not looking for that. Now let's go to the y direction. What's my y initial?
0.5.
What's the y final? 0, right? That wasn't given per se, but the question said how far. It didn't actually say when it hits the ground. I verbalized that. And so when it hits the ground, that's going to be 0 meters because I just chose to set my reference point with ground at 0. You could have set your reference point somewhere else. You have that freedom. But why make life hard? Vy initial from that equation up there. What do we have for Vy initial? Yes. 31.28 meters per second. And what's AY equal to? So there I have my X and Y data separated. And so now I have two problems, but time is going to be what relates the two. How do you suppose I should start this bad boy? Okay? Because I have all the variables except for time, and I need time because that's what ties them together, I will have and I always throw my zeros in immediately because it makes life easier on me. So X final is Vx0 multiplied by time. I don't know time and I don't know X final. So this has two unknowns. That's unlikely to give me something useful.
Why did you stick to the y direction?
I'm going to. But you said X,
Yeah,
so I did it for
like,
X.
the y direction would like immediately.
Right. The Y direction, I have only one unknown because I know all of the variables except for time. And so doing this in the Y direction, I put in my zeros because you know I like to. Y final is 0. And that's it. Huzzah! What kind of equation do I have? I have the quadratic. And you can go through and you can solve for the final velocity, and then using that final velocity in the vertical direction, and then using the final velocity in the vertical direction, you can find the time. But it turns out that the calculation is identical. It actually doesn't save you anything. It just does the quadratic in 2 steps instead of 1. So I did it both ways in practice just to verify that it doesn't save you any time doing it that way. So the quadratic, you have an equation in the form 0 equals a t squared plus bt. Hey, that's not t. Yeah. That's the form of the equation, and then the values for t that make that true are t equals negative b plus or minus square root of b squared minus 4ac all over 2a. Now it's a little uncomfortable because we have ay and a, right? Ay in our equation and a, but they are different, so we can do this. So if I identify things, matching up, and of course I put it in opposite order because I want ABC. What is A equal to? Okay, that is correct. 1/2 AY, which is 1/2 of minus G, or minus 4.90 meters per second squared. What about B? It's Vy initial, which is, 31.2. I was scrolling, forgetting it's right there. And what about C? Sorry, I didn't put the Y0. I'll just put it at the end here. So that means my time is going to be equal to negative 31.28 meters per second plus or minus the square root 31.28 meters per second quantity squared minus 4 times my A, which is minus 4.90 meters per second squared, times my C, 0.500 meters, all over 2A, which is minus 9.80 meters per second squared.
Wait, shouldn't it be 2A?
Right,
Or 2A?
right. Since A is
Oh,
1/2
okay.
G, then 2A is G, or minus 9.8. So there's putting the numbers in. And to make my life easy in preparation, I actually calculated the first part, the minus 31.28 meters per second divided by 9.80 meters per second squared. Those two units, meters per second, divided by meters per second squared. Invert and multiply the units, meters per second times second squared per meter. You're left with seconds, which is good because we're looking for time. And so the first number is positive 3.192 seconds. And then I have plus or minus, and the second number is 3.208 seconds. So that gives us two possible values, 6.400 seconds or negative 0.016 seconds. Which one of those do you think is going to be the time when the ball hits the ground? The positive one. What would the negative one represent physically? An impossibility. If the ball had been projected from ground level, that's the time it would have been projected from the ground level to reach the bat at time 0. That would be the meaning of the negative value. But that's nonsense because that didn't happen. And so this is going to be our time right there. So that's how long the ball is in the air. Then we come back to the x direction and put that in, yeah. So my x final, what I'm looking for is my Vx initial, 34.14 meters per second, times my time of 6.400 seconds, equals, and when you put that in, it gives you 218 meters. Now notice sig figs wise, I kept 4 all the way through, but I only had 3 significant digits. Everything pretty much was multiplicative, so it's 3 in my answer, so that's why my answer only shows 3. Now in terms of feet, that's 717 feet. That would be a home run in any ballpark, right? Even if you were to take the 70% of that, just take the same percentage that we had with our figure above, that would still be, I calculated this out, 498 feet. That'd still be a home run in any ballpark. So why isn't every ball that's hit a home run? Well, the cutting it down to roughly 500 feet would be the in real air number. So why doesn't everybody get hit, 500-foot fly balls every time they're up at bat? Yeah. No, that was what Max said. We already took that into account by lowering it down to 500 feet.
The ball bottom always comes in about the same angle.
Yeah, the angle that it comes off the bat is generally not the optimal angle. Sometimes you hit it too high, well, that's just a deep fly ball. Sometimes you hit it too low, that's a line drive. Sometimes you hit it into the ground, well, that's a grounder. So you have to get the right angle. So hitting home runs is not just about having a high bat speed. Now, people with more home runs have higher bat speeds. But you also have to make good contact and get it off the bat at the right angle. So it's pretty much a very talented athlete who can hit those home runs. It's not just like, oh, he's just extra strong or something. Now, this next problem doesn't look much different, but it turns out to be a much harder problem.
Oh, wow.
You will not have a problem this difficult on the test. Okay, so this one here is a basketball problem instead of a baseball problem. Sports is very applicable at this level of physics. You know, when we're talking about kinematics and soon-to-be dynamics. And I understand sports is not everybody's bailiwick. You know, Russell asked me what an outfielder is. I'm going to believe him that he doesn't know anything about baseball. Because where is he from? Bahamas? No. Bermuda. They both start with B, but only one got hit by a hurricane last week. Yeah.
That's so easy.
Your area of strength. So this is another sports problem because these are the kind of problems that work for it. So if you're not comfortable with sports, it shouldn't be a drawback. It's just the problem is not as interesting. So we have somebody shooting a free throw. So the free throw line, shooting that free throw, probably not jumping. And the stripe is 4.570 meters away from where the basket is horizontally. And this person is releasing the ball from a height of 2.44 meters above the floor. Now, just for reference, where's that 2 meter stick? Is that Russell? No. I don't see. There it is, yeah. So 2.44 meters is not going to be achieved by me. 2.44 meters is releasing it up here. Now, if I jump, I suppose I can release a jump shot from there. But clearly, we're talking about a basketball player who's taller than the average schmo. So, and this comes from the homework site, and they have a range of answers, and this is on the high end. This is basically Shaq shooting a free throw, okay?
So it's not.
We'll talk about that when we get to the solution, okay?
Okay.
I mean, they do go in like 60% of the time for Shaq, right? In practice, they went in like 90% of the time. Yeah, I know. Okay, so we have somebody shooting free throws. We have the speed that the ball is coming out of the hand, and we're asked what angle does it need to be shot from for it to go in. Now, unfortunately, when I assigned this problem, they only had one of the two possible angles because you get two answers. Why do you get two answers? Yeah, you could be above or below the angle for maximum distance and get the shorter range. So either one works. Yeah, I'll answer it now. Why was Shaq so unsuccessful typically at free throws?
His angle wasn't optimal.
He took the low angle instead of the high angle. Right? He shot flat free throws instead of high arcing free throws. And so he could have it dead on and it still hits back rim and bounces off because it's coming in too flat. Okay, so that's it's something that makes it actually, I think, easier for shorter people to make their free throws. So let's look at this problem. What's the first thing we should do? Draw a picture. On the last three problems where you have the option of partial credit, if you're getting partial credit and you don't have a picture, you've already lost, 2 or 3 points. And the picture needs to be, I think it's 2. The picture needs to be relevant. It needs to, help you in the solution. So I'm going to have here the ball starting at and I'm not going to draw the person just because you get the head and the ball confused. And so that's starting at y initial is equal to 2.44 meters. And then the ball is going to go up in the air, come down here, and go through the hoop that is at y final is equal to 3.050 meters. And I'm sorry, x0 is equal to 0. I heard the basket. 4.570 meters is x final. So I've got my x initial and final, my y initial and final. There's 2 more things I know, one that's given and one that is implied. What's the given?
The ball's thrown with an initial speed of 7.15 meters per second.
Right. And the one that's implied is now what do I need to add to my picture? What? No, I'm not going to add the basketball player. I need to add my x and y directions. Okay, so there I have a complete picture with all the information given except for V0 is obliterated. What are we looking for? We're looking for the angle at which it is launched. So we're looking for theta. That's what we're looking for. So now I have everything laid out in my picture. Now I need to do my physics. What type of problem is this?
Can't you still break it up into components and do the anti thing of it or whatever with the sine? Yeah, inverse. And then the inverse of it and then get it.
So far, this looks pretty much the same as what we did before, except for now the first time we solved one component for time and put it in the other one for distance. Now we're solving one component for time and put it in the other to find angle. It seems like it shouldn't be any harder, but I told you it's much harder, right? So let's do the work and see why it's harder.
Using a different equation.
Actually, I'm going to use the same equations. So in the x direction, what's x initial? 0. What's x final? 4.570. What's vx initial? No, it's not so easy. That's the v initial. We need the component. And so just like before, we would have, okay, here's v initial. There's my x component. There's my y component. There's theta. Once again, the adjacent side is vx initial, but we don't know theta. And vy initial is going to be v initial sine theta. So all I can put here really is v initial cosine theta. I could put in the number for v initial, but I still have the unknown of theta there, so I'm just leaving it like that for now. And what about acceleration in the x direction? Okay, going to the y direction. What's y initial? 2.440. What's y final? 3.050. Why am I ending these with zeros? Sig figs, right. Vy initial, we just said that's V initial sine theta. Ay minus g, or minus 9.80 meters per second squared. Okay, once again, nothing looks hard so far. I will go ahead and use the x direction to solve for time. So I have,
You can't, right?
Why did you choose those?
I'm going to do both of them, but the x direction is going to, both of them are going to have time unknown and theta unknown. So both x direction and y direction are going to have two unknowns.
Can you put the
And x direction is the simpler one.
Can you use simultaneous equations to solve it?
Can I use what?
Simultaneous equations and plug one in.
You can. I mean, that's fundamentally what we're doing, but they have trig functions in them.
So for this one, the x direction is easier because the acceleration is zero, so more things will cancel out.
Yes.
Okay.
Or not cancel out, but zero
yeah,
out.
yeah.
And so solving that for time, I have time is equal to x final over vx0. Now I'm just leaving it like that to make it easier for me to write as I go further, because it's shorter to write that than to put in the numbers and have the cosine theta. Now if I go to the y direction, I guess I should write the same. I'm going to put this in the quadratic form already. So there I've substituted the blue is for time. But I mean, it'd be nice. This is where it gets hard. This is where the difficulty begins. So there I've made my substitutions. And what do we have? And now is when you start to hate life a little, because you had tangent and 1 over cosine squared. Randy. You could write secant squared. It does not matter. It still means the same thing. And secant squared is not equal to tangent theta or anything like that. What we need to do is find a way that we can make those trig functions so they are arguments of the same thing, basically. And so what we're going to use is an identity that everyone knows, but probably wouldn't think to use here. Right. Sine squared theta plus cosine squared theta is always 1. Tangent squared theta plus 1. Now, if I write that in, okay, so I just replaced 1 with sine squared theta plus cosine squared theta. Yeah, sine squared theta plus cosine squared theta is always 1. And then sine over cosine is tangent. So sine squared theta over cosine squared theta is tangent squared theta. And cosine squared theta over cosine squared theta is 1. This is why it's hard, right? Who would have thought of that right off the bat? Yeah. That's why I'm not going to ask you something like that on the test, because you'll just take the entire period to solve it and you won't get the other problems done. So the last two terms, I have substituted 1 plus tangent squared theta. And so I have the term with the 1 and the term with the tangent squared theta. And now I have a quadratic in what variable? In tangent theta, actually. I have a quadratic in tangent theta. So if I write this in the quadratic, I have there is my C. Whew. B was simple. Now, because there's only 3 minutes left in the class, if you put in those values and substituting what Y0 is, what Y final is, what G is, what X final is, and what V0 is, you plug in all of those, you end up with, so jumping just to the solutions, tangent of theta is equal to either 47.49 degrees or 50.11 degrees. Now, once you get to using the trigonometric functions, our significant digits calculations kind of don't do it right anymore. So I just put 4 digits here because that's, after all, what you're going to put on your homework if you were to do this problem. You have 2 possible answers. What would you do to make sure you're right? You check it. I looked at these and I wasn't fully convinced that this was right. So I went back and I checked, and sure enough, both of them, if I have the distance set right, then I get the time from my first time equation. And then I calculate the height, and it gets the right height, and it gets a downward velocity, because it's kind of important it's a downward velocity when it goes through the hoop, not an upward velocity. And so both of these are, in fact, the correct answers. And based on this, what angle would likely be the angle where you get the optimal distance with this height, shooting from that height? Optimal distance would be about halfway between those two. Optimal distance, like, so you're back, you step back and use the same speed and use that angle.
Would this be a type of problem that would end up on the test?
No, like I said, this is harder.
Okay, because I was like, I was supposed to know those identities.
Okay, I'll let you out a minute early rather than starting a new section.